Hey, physics people. I want to go over what you're going to see when you do your lab. So we're going to do a little practice. And what we're going to do is we're going to see what happens to kinetic energy when we change the mass, and then go back and start over, and then what happens to the energy if we change the velocity. Okay, we're going to need these things for our lab, so I just want you to kind of follow along and fill out your handout. Pause it if you need to along the way. So first of all, in this first example, we're going to be changing the mass. So I want to point out, if you notice, that the mass is getting bigger as we go down. So we're changing the mass on purpose. So if we go over to the variables there on the right-hand side, notice how this says the mass changes. And because we are changing the mass, we are putting more weight on the cart every single time we do this. That's called our independent variable. Okay. Secondly, the velocity is staying the same. Notice how that there's no changes in the velocity. They're always 3. Okay, there's no change. And when we don't change something, that's called the constant variable. We're going to use the equation, the 1/2 mass times velocity squared, right? We're going to use the kinetic energy equals 1/2 mv squared equation. That's how we're going to figure out the kinetic energy to put in our chart. So we're going to take mass times velocity, and we're going to square that number, and that's going to give us our kinetic energy. Okay, so that's where those numbers came from. So again, in the variables, it says kinetic energy changes, but we didn't know how much it was going to change. We just knew that it was. That makes it the dependent variable. Okay, so get that filled out, and then we will move on to the next part. So for the next part, we're going to be talking about the graph that is created. So notice I took the masses that I had already predetermined, right? I took the mass that was here and I copied it to the mass category, right? And then I took the energies that I calculated and I put those in the energy category, right? So since that's what I have, that's how I get this little chart that I have going on here, okay? That's how I determined what goes in what category, okay? So I went through and I plotted those points, right? So when I plot those points, I'm taking the fact that the mass is 1, so I go down to 1. And the energy was about 4.5, so I go up to about the 4.5 mark somewhere. You can estimate a little bit, and where those two come together, that gets a data point. So I went down the whole list and I did each point like 1.5, right? That's like right here, and 6.75, that's, you know, a little bit farther, not quite 8, you know, somewhere around the 7, right? There. So I put a data point, right? So I went through and plotted all of those. And then after they were plotted, I went ahead and connected them using a ruler, okay? Using this, I'm able to even estimate what my equation is, right? So all equations are y equals mx plus b. So to figure out the slope, right, I took the rise over run between 2 data points, right? And that becomes my slope. So that's where I got 4.5 for the slope, is I just evaluated rise over run of 2 points on my line. Okay, so y equals slope x and then my y-intercept, right? Well, if I have a mass of 0, then my energy is going to be 0, right? If you don't have an object, it can't move, right? So that's where I'm getting the y-intercept of 0, okay? So this is just me doing a rough, old school rise over run application, right, that you used to do in like Algebra 1 or whatever. Now, here's the tricky part, writing the specific and general math models. So let's look at the units of slope for this graph. Okay, we know the units of slope are the rise units, joules, over the run units, kilograms, right? That's where I'm getting rise over run over here, okay? Now, that doesn't tell me much. But if we look back at our notes, we found out that joules are really newtons times meters. Okay, that was what our notes told us, right? So we're basically taking an identity or transforming joules back into its elemental pieces, right? We can do that again. One more identity basically is saying that N is a force, newtons is a force, and forces are mass times acceleration. So I'm able to take newtons and change it into mass times acceleration, right? That is newtons broken down. And then I have this other mass, which is just mass over 1 or whatever I want to do, right? And basically, based on this, mathematically, I see that kilograms are going to cancel. So I'm going to have m times m, which is m squared, and s squared. So I'm going to have m squared, s squared, all right? Those are the units of my slope, which are kind of funky, right? We've never really seen that before. But let's think about it. If m over s is velocity, so m squared over s squared must be velocity squared, okay? So based on all of this, I'm able to figure out what my slope variable was. Let's use those to make my math models. Specific math model uses numbers, right? So I have y equals mx plus b. Well, my y was kinetic energy. My x was mass, right? I can put those down right away, right? My slope I determined was 4.5. But then he needs a label. So that is why I did this piece. This piece has got to come over and become his label, right? Let's see if I can squeeze that in here. And there, my friends, is my specific math model, right? Because my y-intercept was 0, I don't have to put anything for the b, right? If I wanted to, I could say b is plus 0 joules. A number gets a unit, right? There you go. Okay. Now, the general math model means change everything into variables. All right. So conveniently, K is already a variable. Mass is already a variable. All I need to do is change this into a variable, right? So if meters squared seconds squared is velocity to the second power. That is the variable that is represented by those units. I could do one step further and say that this part was my y-intercept or my initial kinetic energy, right? Or K0, Ki, right? Doesn't matter. So that's how I do my general math model. All right. Okay. So we're going to do this again. So this is what happens when we change mass. Mass is a nice straight line and the equation lines up nicely. But things are a little different when we go to velocity. Okay, when we change velocity, remember, so now we're going to keep the mass the same. Mass is no change. No change means constant, right? We are going to purposefully make the object go faster. We're going to make it go faster on purpose. That's the independent variable. We caused the change. And then we're going to use our calculation to determine how much energy we're going to get. We're going to use the calculation and we're going to be surprised by how the kinetic energy changed. So that's the dependent variable. Okay. So I'm going to take those things and I'm going to put them in my chart. This time, remember, this time I'm taking my kinetic energy and I'm taking my velocity, and I'm not using mass, I'm using velocity this time, and I'm going to put those in my chart. And I'm going to take my chart and I'm going to, I'm going to make a little graph here, right, based on what this is. Scroll up. Okay. So when I plot these points, I'm going to notice that I can't run a ruler through them. They're not a straight line. They're actually going to make a nice quadratic curve, right? It's kind of a scoop shape. All right. And that's okay. That's what happens. But here's the problem. I can't write an equation for this, okay? This equation, when we do the lab, we're going to use Google Sheets, and this equation is going to be something, it's going to be some number, but our x is going to be to the second power, right? It's going to be some weird equation. So we can't really do our math on this unless we're like pre-calculus level math students, okay? So let's not hurt our brains and try to do this. There is a way to straighten out a curved graph, okay? And we take a curved graph and make it straight by a process called linearize. Okay? So basically, if we take a curved graph, right? If we take the x values and stretch them out, what that does is that takes that curved graph and straightens it out for us. Okay, so we're going to linearize our information. Now, the way we linearize a quadratic, all right, is by keeping the y value the way it was. We're going to leave our energy the way it was, but we want to stretch out the x values, right? We want to stretch those out. So the way we're going to stretch it is, because it's a quadratic, we're going to take our x values and we're going to quadratic those. We're going to take our x values, right? And we're going to square them and put them back in the chart, right? So if I look at what's going on here, notice I've taken my x values, and even in the title, it shows that I've squared everything. I'm not velocity, I'm velocity squared. Even my units got squared. And I took each of the velocity numbers and I squared them and just wrote them down again. So the y values didn't change, but the x values got squared. What that does is it stretches them out, okay? And then I replotted those points on a new graph, right? I took the new velocity, right? All my new velocity stuff. And I'm sorry, I kind of messed up the numbering. So if you want to fix your numbering, you can. I forgot how to count by threes, my bad. And so if you want to fix that. And then I just replotted those points. And you're going to notice that if you replot those points, you get a straight line, which is what we want because we can deal with straight lines. Straight lines are simple, right? And once I have a straight line, I can go back to do what I did before, and I can do my rise over run, right? And I can create my new equation, right? I can get my rise over run going on here, and I can get my equation, right? And then I'm going to go through and figure out the units and variables of slope for this the same way I did before, except this time I have to watch out, okay? My units of rise are joules. My units of run are meters squared over seconds squared. That's okay. I'm just going to let that follow all the way through. Notice I didn't change the bottom. Notice on the top, I employ some what they call identities, right? I'm going to change joules into newtons times meters. And then I'm going to change newtons, right, into my mass times acceleration. F equals ma. And I'm going to notice that m times m is m squared. So the m squareds cancel. The s squared cancels. So the only thing left over is kilograms, right? So when I go to do my specific math model, right, I'm going to have my y equals mx plus b. Well, my y is kinetic energy. My x is velocity squared, okay? And then I'm going to put my slope, my rise over run that I calculated, okay? Put your rise over your run in there. 1. Numbers need units, okay? So I'm going to take these units, and that's 1 kilogram, okay? All right, so there is my specific math model. To write my general math model, I need to just change this into all variables. Well, that is a variable already. That is a variable already. All I need to do is change this guy into a variable. Kilograms is mass. So if you notice, the general math model for both things is basically our kinetic energy equation. Kinetic energy, mass, velocity squared, right? If you flip to the last one, it was the same thing. It was energy is velocity squared times mass, okay? So the general math model should be our generic equation that we've been using the whole time, okay? Specific math model means put your numbers in it, all right? So fill that out and then go to your student view and answer your big 5 questions.